All right, let's talk about forces. So here's a brief intro video to what forces are and just a little bit about them. So basics of forces. All right. So first thing you need to remember is force is are vectors, and vectors are things that have magnitude and direction. Right. So remember, a scalar has a magnitude, which is just a size, right? But a vector has a magnitude and a direction. So if you were hoping we were never going to talk about that again, you're wrong. But it's just a definition thing, right? It's not like the most important thing in the world, but you need to know that when we talk about vectors, when we talk about forces, they're going to have both magnitude and direction. So size and they're going to point in a direction. Okay, so here's an example. We usually use arrows to represent forces. So here are two different arrows. One's about twice as big as the other one. And you can see that the twice as big one is going to have a larger value, okay, and the smaller one's going to have a smaller value, and they're both pointing to the right, so they'd both be acting in the rightward direction, okay. Oops, forgot to change over. So this would have maybe a value of 30 newtons. Newtons are the unit of force, and we'll talk about that in a sec. And then this one's going to be about half as big, so it'll be about 15 newtons, okay? So that's kind of how we would talk about those and which direction. They're both pointing to the right, so we'd say 30 newtons to the right or 15 newtons to the right, okay? So big force to the right, smaller force to the right. Okay, so what the heck is a newton? So a newton is the unit we use for force because a lot of the work that was done talking about what forces do was done by Sir Isaac Newton. So if you know Newton's laws, the first law of motion: object at rest will remain at rest, or an object in motion will remain in motion unless acted upon by an outside force. So that's basically the rule that forces cause acceleration. So side note, forces cause objects to accelerate. Okay, and we'll talk about that later in the next video, but that is something to know. All right, so let's talk about what a newton actually is in terms of like what units you guys know about. So a unit of a newton is how much force it would take to move 1 kilogram of mass at 1 meter per second squared acceleration. So it would make 1 kilogram accelerate by 1 meter per second squared. So a newton is actually equal to 1 kilogram times meters per second squared. That part probably doesn't matter too much. We're going to use the unit of newtons in this class. You probably won't have to deal with it very much, but in case you ever have to do a conversion, you can convert units and just say that a newton equals this. So let's say I'm looking for, like, I do a problem and I'm looking for seconds. So how many seconds is it? Right? And I only give you newtons. Well, you can convert newtons into kilograms times meters divided by seconds squared. And then through algebra, you could try to find S, the number of seconds, right? But I would also need to have given you, how many meters and how many kilograms. But if I give you enough information, you might be able to solve a problem like that. Do you need to do that? Probably not. Probably not until high school physics, but it's there in case you wondered. Okay. All right. So, what are the types of forces? There are two different categories that we put forces into. There are contact forces, which are the forces that involve touching. So, objects need to be touching. And then there are the long distance forces or the range forces. And sorry, I'm having a hard time making letters. That looks like larg. Long distance forces. So, contact forces involve two objects that are touching. Okay. Long distance forces are the forces that can still act even though nothing is touching. So take a second, pause the video, or if there's a prompt on Edulastic or Edpuzzle rather, then answer the question. What do you think? What forces do you know of, and would they be contact or non-contact or long distance? Okay. Onward. Okay. So for this one, I'm going to write on the left side the abbreviation for this type of force. And then on the right side, I'm going to give you an example. Okay. So these are all the contact forces that we're going to talk about in my class. Okay. So remember, these are the forces that are touching. So applied force, which we would show as capital F for force, and then a subscript capital A for it's an applied force. Okay. So that's normally how we're going to do it when we talk about forces. When we write them, we're going to write big F for it's a force, and then a little letter underneath the subscript letter, either capital or lowercase, depending on what we're dealing with. That's going to tell you what type of force it is. Okay. Normal force is the same thing. It's force in. So force normal. What kind of force? It's the normal force. Tension. It's a force. What kind of force? T. Friction. It's a force. But do you want to make two Fs? I mean, you're going to have to. So I make a lowercase script S like that, or F rather, like that. And then drag is actually the same thing as air resistance. So I usually write FAR. You could write FD and that'd be totally, totally okay. It kind of looks like a P, and I don't know, that's confusing for me, or an O or a circle. So I just write FD for my happiness. You can do it, or FAR. So you can write whatever you want. It's fine. Okay. So what the heck is an applied force? Let's say you're standing on the ground and that's you. Okay. And there's a chair and you're going to push the chair. That's an applied force. You're applying a force to the chair. Or maybe you're a person and you are going to pick up an object, right? The force you apply to pick up the object, I don't know how I would draw that, but let's say you apply a force upward on the object, right? That force is your applied force. You're applying it. Okay, normal force. There's two situations where you talk about normal force, and there's more than two situations, but there's many situations. Anytime an object is resting on a surface, so let's say we have a box on the ground or a box on a slope, okay, that slope or that surface, whatever that surface is pushing up on the box at a 90-degree angle. Okay, it's applying a 90-degree angle force to the surface, to the box. So you see here, when the box is on the ground, it's like this. When the box is not on the ground, it's like this. Now, the state standards say I don't need to tell you about this because it breaks the rules of like what is your normal motion, which normal motion or one directional motion we'll talk about like up, down, left, right. This is up and left at the same time, but we're going to talk about it anyway because we're smart. Okay, tension. Tension's easy, right? If there's a rope and it's holding something and that rope is taut, there's tension. So let's say there is a rope in gym class and you are trying to climb the rope. I don't know why you are horizontal like this, but let's say you are. The rope is pulling up on you with a tensional force. Okay? The rope is pulling up on you with a tensional force if you were the object in question here. You would then be pulling down on the ceiling, right? The rope would be pulling down on the ceiling with a tensional force, but we'll worry about you first. Okay, friction. Let's make a bike, shall we? It's a beautiful, beautiful bike. It's going to be really good. You guys are going to love it. Here's a bike, and that's what bikes look like, right? Got a little seat. There's probably pedals back here, and they somehow connect to the back wheel to make it go. Great. All right, Pog. All right, here we have a bike. So this is our bike. When you're riding your bike, you notice that you have to, pedal, otherwise it will slow down. Why does it slow down? Because the bike's in contact with the ground. What's happening between the tires and the ground? Well, there's rubbing, right? And that is friction, and it usually works in the opposite direction of motion. So if you're trying to make your bike go forward like this, friction is going to be working to not do that. Okay, so if you let go of your bike pedals, if you stop pedaling, you're going to eventually slow down, right? Because of friction. Okay, what the heck is drag? It's literally the same stuff. It's just friction of the air. So when you're pedaling your bike, okay, and you stop pedaling your bike, as you're pedaling, you'll feel the wind blowing in your face, right? If you stop pedaling the bike, that wind will get less and less and less because that's the air resistance. Air resistance comes from the particles in the air that are pushing into you. So same thing's true if, let's say, I don't know why this person is going to have now like an actual torso, but we're going to give them one. And you're skydiving, right? Give you a little, there's your backpack so that you're safe. Okay. And there's a parachute. You're skydiving. You're going downward, right? So that you'll feel the wind blowing in your face, right? That wind blowing in your face is air resistance. It's keeping you from just flying into the ground really fast. I mean, obviously you still will, unless you pull your parachute, but air resistance is there for you. If there wasn't air resistance, people would not be able to fall with parachutes because their parachutes would not fill up with air. Good thing there are air particles around, right? So that's what drag is. It's kind of like air resistance. Didn't mean to cross that out. Sorry. Okay, that's that. Moving on. Long distance forces. There are three. We're going to talk specifically about one, and it is the force caused by gravity, which is also going to be called weight. Okay, so we're going to abbreviate that as F little g or W. Okay, they're the same thing. The force caused by gravity is equal to your weight. So gravity is a force that's acting on you, even if you're not touching a surface, right? If you're up in the air, gravity's still pulling you down. If you're out in space, you're still getting pulled somewhere by some gravity from something, right? We're going to talk more about this in detail later, but this is the one long distance force that you do need to know about. There are two other ones. Here they are. Electrical forces, okay, and magnetic forces. All right. Now, these do exist, but I'm not going to ask you about them in the very near future because they are complicated, and I'm not going to have you have like a box that's on the ground, but also full of magnets, but also levitating, and then also there's like an electric wire and there's electricity running through it. I'm not going to mess with you that way. Okay, that would hurt your brain, and it hurts mine to think about just now. So the way we're going to explain these is we're going to explain how things that aren't touching can act on each other using this thing called a field. So there's a magnetic field, a gravitational field, an electrical field. We'll talk about that later. Right now is not the time. But gravity, it's a thing. You should know about it. It's acting on everything. Okay, last thing. So here's a really, really complicated example. All right, we've got a rock climber, right, attached to a rope. There's a partner down here on the ground holding onto them. We have modeled all the forces acting on the rock climber. There's gravity pulling them down. Their foot is touching the wall. So the wall is applying a 90-degree force to the left called the normal force. Their foot is dragging on the wall as they go down. So there's a frictional force there. And then also this rope is taut and it's pulling on you. Okay, this is a really crappy drawing. I'm sorry, but pretend that rope is taut. There would be something called tension, right? Pulling you up and to the right a bit. Now, this is really complicated and confusing. So instead of making it like this, where we draw the picture every single time, you may draw a picture or there may be a picture for you. But to make it easier, we're going to use something called a free body diagram. Maybe there's the lag. Love that. Okay, good. So free body diagrams are traditionally drawn either as a box. So we've taken the whole problem, we take the rock climber and all the stuff, and we make them into a box, or as a dot. Either one is totally acceptable. You can do it however you like. I prefer the dot. So if you want to do what I like, or if my reasoning makes sense to you in a second, that's great. But you can also use the box. Why do I like the dot better? Well, the dot takes the entire problem and smushes it down into one single atom. So all the forces are acting on the same spot, the same thing in space, instead of acting on possibly different sides of a box, right? Which for me is kind of confusing because like the force acting on this man will actually, the rock climber will actually make him kind of tumble some, but that's more complicated than what we're going to do. So we usually just use, one single item. So we're taking and we're smashing him down into a single cube and just saying, here's the forces, or into a single atom and here's the forces. Okay. So here's what that would look like. Tension, right? Well, actually, let's just show you a general example, right? Forces would then act outward from the center. So you would do it like this with the box, or if you like the atom model better, all of the forces would just leave the atom in a single from a single point, right? Like that. So this is why I like the atom better. It's just a little bit simpler looking, but you can do it however you want. So if we were to draw the free body diagram for this man for realsies, mistake, sorry, we would then do this. We would say, okay, gravity's acting down. Okay, FG. We would say, okay, normal force is acting, it's very small because he's barely touching the wall. Normal force is acting to the left, right? A little bit of normal force, small, should be straight left. And then friction is acting straight up. Friction's also small because his foot is barely touching the ground, so F sub F. Then we would say, okay, tensional force is a little bit bigger because it's the rope pulling on him, supporting most of his weight. So we would say then, mistake, big F sub T, like that. Okay, so that's how you draw this free body diagram. And eventually the size, the magnitude of the arrows is going to matter because we want the forces to either be balanced or not. But for now, we're just not going to worry about it. Okay, and one really quick tip. I know that I told you a second ago that I'm not necessarily supposed to show you multi-directional stuff. Like this one is going up and to the right, this tension force. So what you can do if you're thinking about it is imagine it like a right triangle, right, where it has a force going right and a force going up, and they combine to make that hypotenuse. That is a totally reasonable way to think about it, and that's how you'll do it in high school physics or beyond. Okay, but I don't want you to see that example because that's about as complicated as I can make a problem, and now we've done the whole thing, so see you later.